Hello everyone. In this video, my objective is to quickly describe the operation of a BJT transistor and prepare you for circuit analysis in circuits that include such transistors, such BJT transistors. So very much like a MOS transistor, the BJT transistor is also a nonlinear device. The physics of operation is different, and as you can tell from this cross-section, this simplified cross-section, unlike what we discussed with the MOS, there is no isolation between any of the terminals and the device, such as the one that we saw with the gate of a transistor, where the gate basically was not electrically connected to the rest of the device. Here we're actually dealing with two PN junctions. There's one PN junction between the base and the emitter, and there's a second PN junction between the base and the collector. And keep in mind, this describes an NPN BJT transistor, and we have the same way that we have an NMOS and a PMOS. With BJT, we also have an NPN BJT and a PNP BJT, which are basically a dual of each other. So the way that this device basically operates, in a sense, is actually similar. So if you remember, with the MOS, the current that would pass from the drain to the source would be controlled by the voltage of the gate source. Now in this device, pretty much the same thing is happening. The current that goes from the collector to the emitter is going to be controlled by the voltage between the base and the emitter. So there is quite a lot of similarity between what the collector does here in a BJT and what the drain does in a MOS, what an emitter does here with what the source does in MOS, and what the base does here with what the gate does in a MOS. So once you kind of understand how the MOS operates, you're pretty much ready to basically deal with any kind of transistor, including BJT. I guess a really good general description of a transistor, any kind of transistor, would be a device in which you can control the current passing through terminal using the voltage of a third terminal. So in some way you can describe them as voltage controlled current sources, and that's actually the model that we're going to use later on to describe a transistor. Once we start doing small signal analysis, you will quickly see that that's the model that we're going to use. We can even use it here, but the model would be a nonlinear model. Now, just a very brief discussion on the physics of operation. The way that the device operates is that if you apply proper voltage between the base and emitter, and keep in mind, base emitter is a PN junction, so it's pretty much like a diode. And if you basically turn this diode on and apply a voltage that is equal to the built-in voltage of the PN junction, which is about 0.6, 0.7 volts for a silicon diode, then this junction turns on, becomes forward bias, and then you would start seeing electrons being injected from the emitter to the base. But then if at the same time you have the proper voltage between the collector and emitter, which means that the collector has a higher potential with respect to the emitter, you're going to have a strong field created between the collector and emitter, and all the electrons that get injected to the base, instead of ending up leaving through the base, they actually get swept away by the collector or get collected by the collector, and then they leave through the collector. So electrons again get injected. Let me use this. So electrons get injected from the emitter to the base, and then instead of ending up leaving through the base, they actually end up being collected by the collector and leave through the collector. So you get electrons going from the emitter to the collector, assuming that the base emitter junction is actually on, which means you have to have the proper voltage, and therefore you get a current going from I goes from the collector to the emitter. Electrons go in reverse direction of the current. That's our convention, and that's all assuming that the voltage between the base emitter is about 0.6-0.7 volts, so that the device is on. Otherwise the device is described to be in the cutoff region, and then also the collector emitter voltage has to be positive. And not only that, in order for us to enter the proper range of operation, the collector emitter voltage has to be larger than a certain threshold. So again, similar to what we did with MOS transistors, I can show the operation of a device, plot the current voltage characteristic of a device on a 2D plot. Generally I have to have more than a 2D because we have more terminals, so the currents are dependent on more than just one voltage, but I can reduce that down to a 2D and show the current of, say, collector IC as a function of the voltage VCE, the voltage between the collector and emitter, but then repeat the same plot for different values of VBE. So we're going to see something like this, and you can actually see that this is clearly very much similar to what we used to see. Now the cutoff voltage is something very similar to the threshold voltage for the CMOS, and it's about 0.6-0.7 volt for normal silicon-based NPN transistors and PNP transistors. But then the criteria for operation in the region that was useful and used to be actually called saturation region for MOS is different. Now, more than that, this region of operation that we would like to have the device operating in here is actually called the active region. And this region that we normally don't operate at is actually called saturation, which is obviously confusing because the region of operation that we normally wanted the MOS to operate at was called saturation, so that kind of throws a curveball at you. It's a bit confusing, but you get used to it. Just remember that this is the region that you want to operate. And the VCE at which this happens, you can actually simplify it and just simply say that the VCE should be larger than a certain threshold. The criteria for MOS was not simple. The voltage has to be like, there was an inequality that we used to use, and say VDS has to be larger than VGS minus VT, so there was some dependency on VGS, but here we just simply say as long as it's larger than something around 0.2, 0.3 volts, you are in the active region. Now, to write the equation for the device, the current of the collector, assuming that the device is in an active region, and in other words the device is on, VBE is about 0.6, 0.7 volts, and VCE is more than 0.2, 0.3 volts, the current of the collector is equal to IS e to the power of VBE divided by VT multiplied by 1 plus VCE divided by early voltage, VA is called. So this is early voltage. Now this voltage, the early voltage, is something that comes from the physics of the device and usually is given in a data sheet or in a problem that you have to solve. A lot of times you can, if you recall, the current of a drain of the MOS had kind of the same dependency. I'm going to write it here just for your refreshment, for refreshing your mind. It was K times VGS minus VT to the power of 2 times 1 plus lambda VDS. So you can kind of see the similarity here, VDS for the MOS and VCE for the BJT, lambda for the MOS, and 1 over early voltage for the BJT transistor. Early is actually the name of the person who kind of for the first time wrote the equation in this form and basically developed this. This is a voltage. Developed the equation in this specific format. Now, for the most part, a lot of times we actually ignore this dependency and just use this part of the equation the same way that we a lot of times assume that lambda is 0. In other words, when you assume that, you're assuming that this line is actually a flat line and the current of the collector is not a function of the collector emitter voltage. Now, nevertheless, this equation is a exponential function, and it shouldn't surprise you because this is basically p-n junctions, and we remember that the p-n junctions or diodes had exponential equations for their current, for the dependency of their current over their voltage. And the advantage here is that then the same way that we could relatively easily linearize this equation and piecewise linearize it and assume that basically once the diode turns on, then the voltage is constant, and the current that is passing through the device is not going to affect the voltage. We can basically do the same here and assume once the device turns on, then VBE, the voltage between the base emitter, stays constant at about 0.6, 0.7 volt. Now, unlike what we had for the MOS transistor, we actually have to have an equation for the base, current of the base, because here there is actually current going into the base, even though it's small for the most part, but there is a current, and this equation goes something like this. Again, beta here is a relatively large number that tells you that the current in the base is much smaller than the current in the collector, and it really comes from the physics of the device. Normally this number is something larger than 100. And so the current of the base is basically 2 orders of magnitude smaller than the current of the collector. So that's about it. This is these two equations define what the operation, how to describe the operation of a BJT transistor when you have a BJT transistor in your circuit. Now, we can actually simplify this set of equations the same way that we did that for diodes, and basically assume once the device is turned on, then the base emitter voltage is constant. So the equations for the device turn into something like this. So instead of that exponential equation, we just assume that the base emitter voltage is a constant number between 0.7 0.6 to 0.7, which is going to be usually given. And assuming that the device is in the active region, then the collector current is beta times the base current. So with that, let's start actually doing a really simple circuit using a BJT to kind of practice analyzing circuits that include BJTs. So let's say this is connected to 5 volts, this is 1K, and this is 6K, and this is 1K again. Let's say VBE is 0.7 volts, and the beta is 100. So with that assumption, I'm gonna start, like always, label the circuit. So this is my ground, or 0 volts. I'm gonna call this my VB. This is 5 volts. This would be my collector, and VE is actually the same as 0 in this specific case. Then I'm gonna call this current I1. Now with the MOS transistor, I used to call this current also I1 because this current was 0, but now here I can't do that normally, or generally speaking, so I'm just gonna call it IB. So therefore this is I2. I'm gonna call this IC, and the current down here IE. Once I do that, I'm ready to write all the equations. So now we have two KCLs, one for this node and one for the transistor as the other node in the circuit. So we actually do have two KCLs. I1 is equal to I2 plus IB. Then for the transistor as a node, IB plus IC is equal to IE. For this to be clear to you, let me just put this virtual node here. So IC goes in, IB goes in, and IE leaves that node. So therefore this second KCL equation. Then we move on to equations for components. For the 6K, I1 is equal to 5 minus VB divided by 6. For the 1K down here, I2 is equal to VB divided by 1. For the 1K in the collector, IC is equal to 5 minus VC divided by 1. Then we get to the transistor. I'm going to assume that this is valid. In other words, the device is on and in the active region. So VBE, which is VB minus VE, and in our case just VB because VE is 0, is equal to 0.7 volts, and IC is equal to 100 times IB. So now let's count the number of equations that we have. We have a total of 7. The number of unknowns, I1, I2, IB, and IC, and IE, 5 unknown currents, and then VC and VB, 2 unknown voltages, total of 7 unknowns. So 7 unknowns, 7 equations. We should be able to calculate that. Now this is actually pretty simple calculation. VB is 0.7. I put it there. So this I2 is basically 0.7 milliamp. I also put it in the first equation of component. That is 5 minus 0.7 is 4.3. So that's 4.3 divided by 6. I can quickly calculate that using a calculator. So 4.3 divided by 6, it's basically 0.716, so that's 0.716, about that. So now I can put this in my KCL, the first KCL, and from this one I can actually calculate IB, which would be I1 minus I2. So IB is equal to 0.016. Now I take that, put it in that last equation. From that, IC is equal to 1.6 milliamp, and from that I can actually calculate VC from here. So that would be 1.6 volts, 5 minus 1.6, so that would be 4 point, well, actually, sorry, 5 minus 1.6 is 3.4 volts. And that's it. Now I have all the unknowns. And IE is just simply 0.7 plus 0.016. It's IB plus IC. So that's IB, that's IC. Where did we calculate IC? Right here, right. Well, we actually haven't calculated. Right down here. IC was 1.6, sorry. So 1.6 plus 0.016. So it's 1.616. As you can see, IE is actually very close to IC, and that's expected because IB is really small. Now, this is the time that I have to go back and check the active region condition. So VCE is the same as VC, and it's 3.4 volts. It's larger than 0.2, 0.3. It's larger than saturation, so the calculation stands. Now, this could have been easily not the case. For example, if this 1K was much larger voltage, then this voltage, much larger resistance, then VC could have been a voltage smaller than 0.2, 0.3, at which point then I had to go back and use a different set of equations, because this is no longer valid. This is only true if I'm in the active region. If I'm not in the active region and the device is on, we're going to use this set of equations. Then VCE is basically just equal to VCE sat. The saturation voltage is a constant voltage that is equal to 0.2, 0.3 something given volts, and VBE is still equal to 0.6, 0.7 again given. So instead of the set of equations that so this was for active, and this is when the device is in saturation. So I go back, and instead of these two last equations that I put here, I use these two equations and redo the calculation. Notice that when the device is not in the active region, the equation between IC and IB doesn't hold anymore. In other words, you don't get a current amplification or current multiplication between the collector and the base, and that's an important observation. Make sure that if your calculation based on the operation of the device in the active region resulted in a VCE less than the saturation voltage, you scrap all that calculation and use this new set of equation and redo all of the calculation again. And no longer use beta, basically. Beta is only useful if the device is in the active region. Hopefully that this has been helpful. We're going to continue doing more with transistors in the upcoming videos. Thank you.